In this video, I will explain you the concept nuclear fission. So as I told you before, nuclear fission will happen with the nucleus having mass number above 170. So the tendency would be more when the value will become more than 200, because above 200 or above 250 or above 170 itself, what will happen? The binding energy per nucleon is decreasing, going to an unstable nucleus. It will always have a tendency to break into two smaller nuclei. Each has got higher binding energy per nucleon. See, here it has got lower binding energy per nucleon, and this, when it split into two nucleus having higher binding energy per nucleon, it will move towards a more stable condition. Okay. So what we will do, we have uranium-238. Okay. Now to uranium-238, we will bombard a fast moving neutron. So what will happen? We have a nucleus here. The moment a fast moving neutron enters a nucleus, see, why can't I use a proton? If I am using a proton, what will happen? You know, uranium-238 is positive charged. Okay, at the same time, when I am throwing a proton towards it, what will happen? This positive and this positive charge, there will be a repulsive force. This will come back. But at the same time, if it is neutron is having no charge. So this chargeless particle at high velocity, that will enter the nucleus. So if this is the initial condition of the nucleus, that will now get into a larger size, because one nucleus has ended, one more person has ended, so the size will become higher. So uranium is having, yeah, I am taking an isotope which is uranium-235. Okay, so this uranium-235, the moment I am adding one neutron into it, that will be uranium-236. So this is, you know, this has got lesser stability, nuclear stability. The moment the stability is less, then that will break into two smaller nuclei. See, this is the initial condition. One more neutron has entered here, so size become higher. Now when the size become higher, the binding energy per nucleon is less, more instability, at that moment that will break into two smaller nuclei. Okay, now the binding energy per nucleon will come here, and at that situation it has got higher nuclear stability. So this is the equation. Uranium-235, one neutron entered, this become uranium-236, and that has split into barium and krypton. See, 144 will come here, 89 will come here. See, here in these conditions it has higher binding energy per nucleon and more stability, and this would release 3 neutrons. So how will you get this equation? See, here number of proton is 92, so it have to be balanced here. 56 plus 36, it is 80 plus 12, 92. And on the top, 235 plus 236. Here also 144 plus 89, and how many neutrons are there? 3 neutrons, so 3 into 1. So 3 into 1 is 3, plus 89 plus 144 will give you 236. Similarly here, 1 plus 235, 236, that would be equal to 133 plus 99 plus 4 into 1. So similarly, balance your reaction. See, this 92 should always be this one. The sum of left hand bottom corner. So this is left hand bottom corner. 51 plus 41 is 92, and 54 plus 38 is 92. This have to be balanced, and 1 plus 236 is 235 is 236, and 140 plus 94 plus 2 into 1 would be 236. So now what has happened? This is conserved, and I mean we have conserved the number of nucleons and even number of protons. What will happen? There is an energy change, right? Here this is the binding energy per nucleon, and that has become this and this here. So there would be a change in binding energy per nucleon. How would you get that? Just multiply 230. There are 238 nucleons here. So 230 into whatever the value of binding energy per nucleon here, multiply that, Now that will become 144 into binding energy per nucleon of Ba and binding energy per 89 into binding energy per nucleon of krypton. So for Kr and Ba, you find the binding energy per nucleon. Per nucleon, that would be binding energy. With the Kr value, multiply 89. With the binding energy of Ba, multiply with 144. Then you will get the total energy available here. And on multiplying 236 with binding energy per nucleon of uranium, you will get the total energy available here. So you will see that this energy is more than the sum of binding energy due to Ba and Kr nucleus. So this energy and this energy have to be conserved. So we have to add energy here. So this plus this would be the total energy here. Now this energy is available for us. We can use this energy. We can use this energy to run a nuclear power plant. Okay. So this is how we are generating energy in nuclear power in nuclear power plant. This is nuclear fission. Okay, fusion will also release energy, but it is practically difficult to use the energy available in nuclear fusion. And the source of energy which we have is sun in daytime, and sun is producing its energy through nuclear fusion. But that process, making it happen here on the surface of Earth, is difficult because, see, I will explain you in coming video, but for that we need such a high amount of pressure and such a high temperature, which is practically difficult to accomplish at the surface of Earth. Anyway, we are able to generate energy through nuclear fission, and we are able to control it and use it for our requirement. Okay, so this is nuclear fission, very, very important concept. Okay, splitting a larger nucleus into two smaller nucleus, releasing energy. Okay, thank you.